All right. I'd like to welcome Rob again back to DLCT for, I don't know, sounds like fourth or fifth time now. And this paper, of course, is all the craze. Everyone's talking about it. I'm sure you guys grouped many other teams' projects. I've heard at least like AI scientists like 8 times across, talking to people because it's such a intuitive name. Would love to hear how this works. And let's get started.
Awesome. Thank you so much, Roseanne, and thank you so much for the opportunity to present our work. As already said, I'm Robert. I'm a research scientist and founding member at Sakana, and at the same time, I'm wrapping up my PhD. And today I'm going to be talking about our recent release called the AI Scientist towards fully automated, open-ended scientific discovery. And of course, this is not my own project, but I'm only part of a bigger team. And this includes sort of Chris Liu and Song Liu, who are not related, just share the surname, and Jacob Förster, Jeff Clune, and David Han. And so basically, when you look at sort of the history of deep learning and generative AI, we've sort of seen tremendous efforts in sort of improving methods, right? So here on the left-hand side, you can see sort of image generation as one example, sort of starting with GANs and VAEs, and then moving towards sort of DALI-style models, diffusion models, and most recently sort of Imagine 3 and Flex 1, right? And sort of what this already shows is that these methods tend to improve in sort of performance quite significantly over time. But when they start out, they're usually quite poor, or at least poor, relatively speaking. And sort of this has been like a trend throughout different modalities, like not only images, but also text, where sort of ChatGPT was like a big moment, but also when you look at sort of text-to-video models like Sora or Veo, they start usually with like some version which is not very, very good, or I guess visually pleasing, but they become sort of, extremely good and actually create value for society in one way or another. And sort of unlike sort of images, text, and video, we've only seen sort of a couple of efforts sort of really doing this for science and scientific discovery, like, for example, AlphaFold, AlphaTensor, or Galactica, or like the recent ESM3 model. And what these methods usually sort of do is they automate one part of the scientific pipeline, right? So, for example, the papers are not written by the method, but the papers are written about the method, right? And so what we wanted to do is we wanted to see whether or not it's possible to essentially automate the entire pipeline of scientific discovery in the context of machine learning using foundation models. Okay, so this is sort of what we're setting out to do. And I think what's really important about this slide is to sort of keep in mind, again, that these things start out sort of as base versions, and then they improve over time. And there are many, many reasons for that, including sort of the collective effort of our community to sort of democratize these tools and techniques and methods and models, as well as to sort of improve them and ultimately also validate them. Okay. And as I was already saying, there's a lot of work on sort of using foundation models to automate certain parts of the scientific pipeline, right? So, for example, there's work on using language models to design reward functions, for example, in the context of Eureka and reinforcement learning agents. There's work on using foundation models for architecture search, like evo prompting, or to discover new parts of mathematics or code in the form of fun search from Google DeepMind. And so before this project sort of started, me and Chris actually worked on sort of the predecessor, which actually tried to use foundation models to discover preference optimization objectives, right? So here, basically, as you can see on the left, we use a foundation model to output code proposals of objective functions. We then use them to train some model, and we can then evaluate them and sort of use the information that we gathered when evaluating the code and sort of a type of fitness in terms of the performance to update the context, and then sort of run this in a type of meta-discovery loop. And as I already said, all of these sort of methods only use essentially a foundation model for one part, namely sort of the discovery of code or snippets or augmenting one part of the scientific pipeline. But when you look at science more broadly, right, there are many more steps in there than just sort of writing code, right? There's sort of the whole notion of first problem identification and sort of thinking about what is an important problem to work on, sort of coming up with hypotheses, what one could do in order to improve upon sort of the problem or make it better. There's sort of communication with other researchers about sort of the approach that one comes up with, and then there's an actual experimentation stage with iteration and sort of discarding hypotheses and so on. Furthermore, there's a whole sort of ecosystem built around the scientific process, including reviewing and sort of the researcher taking the feedback, improving upon the manuscript, and sort of resubmitting. And then at a final stage, there is also like the whole process of publishing, as well as then sort of taking what has been published to sort of make it diffuse into society and more broadly to get it adopted or used by people potentially. Yeah. So what we wanted to see is whether or not we can at least automate the majority of this, right? So we're not yet at sort of knowledge diffusion necessarily beyond sort of publishing a manuscript, but we wanted to see if we can leverage foundation models to come up with scientific ideas and execute them in terms of code, as well as write papers and even potentially use another agent to evaluate sort of the scientific content and perform some type of review. And maybe as a note, if you have questions regarding sort of understanding and the method, it would be great to, you can just sort of raise your hand and we can take the questions during the talk. But if you have sort of more, I guess, ethical or broader discussions in terms of philosophy, it would be great if we sort of do them at the end. So thank you. Yeah. Okay, so this is sort of the high-level motivation. Can we take a foundation model and try to automate large parts of the scientific process in the context of machine learning? And yeah, so the idea is essentially, can we press a button at the end of night and at the end of the day, and then have a autonomous AI scientist go out, test hypotheses, and try to come up with novel approaches to problems we're interested in. And the AI scientist, the pipeline that we propose, sort of comes with multiple different stages, which are all driven by foundation models, where sort of the three main stages are the idea generation stage, where we have an LLM propose a new idea and plan experiments to run. We check essentially the novelty of these ideas using semantic scholar, and then we score sort of what idea to evaluate first. And afterwards, there's the second stage, namely experiment iteration, where given an experiment template, like for example, training some endless classifier, we implement the idea. Let me maybe skip to the next slide. We implement the idea using code diffs via a software agent tool called Ada. And then after sort of the implementations are done, we execute the experiment. This usually saves some type of result, let it be plots or just data. And then after an experiment has been run, we show essentially the agent results, and the agent can update the plan for experimentation. And then in the end, given all the numerical data and the plots, we use another manuscript template, like for example, an ICLR conference template, and have the LLM agent essentially output text diffs, right? So it can then write about the results, and it can also grab citations from the internet to essentially, write a related work section, right? And then given this manuscript, we can then extract the text again, feed it to an LLM agent, and obtain a type of review, right? So basically, this review would suggest what kind of scores it would get the paper, and this would be similar to like a conference review that we would receive, like with weaknesses, strengths, and so on. So this is the high-level pipeline, and now basically in the next minutes, I'm going to go through sort of each of these stages and discuss sort of in detail what's happening. So let's start out with sort of the idea generation stage. So Maybe as a sort of footnote, this talk is not going to be very technically deep. Okay, so there's going to be literally 0 equations. This is all just going to be sort of prompt and engineering tools for sort of iterating over prompts, like, for example, reflection, chain of thought reasoning, and so on. So basically, the idea generation stage starts out with a type of code template. Okay, so like I was saying, think about like MNIST classification, or for example, training like a small transformer using Kapathi's NanoGPT repository, right? And then basically there's a single file called experiment.py where where the experiments are implemented in, and we parse that experiment file into text and then ask a foundation model to essentially propose a new novel idea, given sort of potential previous ideas, to sort of conduct as research experiments. Okay, and I'm going to show you a couple of examples of these ideas that pop out next. But basically, we generate these ideas and then we cross-check whether or not they are novel using semantic scholar, right? So basically, we generate a set of ideas, and then afterwards, we have an LLM score the ideas by novelty, right? So this could, for example, be related to like whether or not there was previous work out there before about it, or whether or not it's feasible, or yeah, what kind of results one could expect from running this experiment. So we try to filter the paper novelty via cross-validation with semantic scholar. And then afterwards, we get an idea like the one shown here, where we have a basically JSON dictionary with different keys, where, for example, here, we're interested in implementing something called adaptive dual scale denoising in the context of 2D diffusion, where basically we augment a simple diffusion model with sort of a second branch, which acts at a different time scale, and we have to sort of predict different weights given sort of the input features. And as you can see in here, there are sort of scores for interestingness, feasibility, novelty, and whether or not we should actually implement the idea going on. And afterwards, given the idea and the experiment outlined here, we then continue to essentially move forward to the code implementation stage. So as I was saying, are there questions? Sorry.
Can I have a question there? So the JSON is generated. Do you provide a template to tell the model which fields to fill?
Yeah, so we're basically telling it, okay, here's a previous idea, which looked like this. And then we tell it what to essentially put into the different fields. Like, for example, the name should constitute the name of the idea in some sense. Yeah, exactly.
And so it looks like in the prompt, you use like few shots. You gave them a few ideas they generated before. Previous idea string. So that all actually generated by the model, or you just took a few human generated ideas?
So for most of the cases, this is a single idea that we either like manually constructed or was generated from a previous run, right? So there's not a lot of burning in some sense happening. Yeah, it's just sort of an example of how to follow the template, basically.
There's a question in the chat. How do you ensure the ideas are novel?
Well, yeah, that's a good question. Like I was saying, there is a type of semantic scholar API built into this agent where we try to check online whether or not there is very, very similar work already done, right? And then given sort of the results from the API call, we can then have the LLM essentially score the novelty again, right? So we then only select the ones which are novel and which are sort of the most fruitful, or yeah, the most interesting. What is the similarity measure to measure similarity? Well, there's no like Hamming distance or something we use to compare strings from ideas, right? It's more like in some sense we create a query which summarizes sort of the idea, and then we check on Semantic Scholar if other ideas are there that sort of are very much aligned, right? So this is all done sort of using Semantic Scholar. Can you give an example of an idea string? Yeah. So this is basically what I was showing here, right? So this is quite literally the output that you receive from this idea generation prompt, right? So having a name, a title, an experiment outline, and these different numerical scores for interestingness, feasibility, and novelty. Wondering at level of scope these ideas are, and if there is diversity in that. Yeah. So in the paper we have like more than 50 ideas for each of the templates that we use, and when inspecting them, you can see quite a lot of diversity, right? So some of these are simple sort of projects, I guess, like a master student would do, like in the sense comparing sort of architectures or running simple ablations. But some of them are actually quite nuanced in the sense that yeah, I would be interested in the results, right? So I'm going to show you like one of the examples, which relates to something I did previously in my PhD, and I was yeah, pleasantly surprised. Yeah. With respect to the field. Well, how is a big question, right? This is sort of the output of the LLM, right? So I can't really speak to the inner workings that much, but I can say that when sort of manually inspecting these scores across ideas, they were actually fairly accurate. Is the idea generation generated hallucinated fully by the foundation model and use any papers for inspiration? So we don't provide few shot examples of entire papers, right? We provide this one example to essentially tell it how to follow the template instructions. But I guess hallucination in this context is almost like a good thing, right? In the sense that it's a creative thing of coming up with a new idea. Okay, I'm going to close the chat for now and continue with the presentation. Yeah, so once we have an idea, we then go on to actually implement it in code, right? So I was already saying that the starting point of the AI scientist is a code template, basically, that we provide upfront. So you basically, as a human researcher, set the seed for what sort of research should be done, or on what research should be done. And then afterwards, given the experiments, we implement code diffs to the template, right? So this is, again, done using an LLM and using Aider as a software developer agent, essentially. And if you don't know about Aider, I think you should. It's a really great open source project, which is leading on the SWE benchmark and uses essentially a bunch of intricate ways for prompting and caching different sort of instructions, right? And we leverage Aider together with sort of both frontier closed source models like GPT-4o or Sonnet, but also with Llama and DeepSeek Coder. And I'm going to show you some comparative results for these different foundation models in the next couple of minutes. Okay, and in order to run such an experiment or to implement the experiment, we basically provide the title, idea, and a maximum number of experiment runs that can be executed. And we instruct the foundation model or the coding agent to essentially list the experiments which should be run, and then implement them sort of yeah, iteratively, right? So we tell it the number of resources and how often it can execute essentially this experiment.py file, and then it has to implement iteratively sort of the different code level changes that we want to see in order to implement the experiment. Okay, so here is now an example for the idea that I showed you before, right? Where you remember we had to implement, or the idea required implementing a global network, a local network, and a weight network. And as you can see here in green, basically given the base template, the original neural network architecture is replaced by sort of these global networks, local networks, and the different weight and the weight network. And then also in the forward pass, so this is PyTorch code, you can see how these things are then sort of used when processing input. So here you can already see this is just one example, but like there are many more in our repository where Aider is actually quite capable of implementing most of the ideas that we come up with. Okay. After these experiments are run, so after we generate iteratively sort of results for the plan, we can use the numerical data and the plots that were generated together with a manuscript template to again sort of summarize or write code diffs into that template. And then afterwards, it can just be sort of compiled using LaTeX, for example. And here we're sort of also, again, providing a template. And this template is based on Jacob Förster's How to ML paper guide, right? So basically, Jacob once upon a time wrote a very helpful document to the community where essentially he outlines how to structure a paper, right? So this includes things like how to write an abstract, how to write an introduction, how to write related work. And these types of instructions we're repurposing as sort of prompts for writing a paper. And as you can see here, the prompt goes as follows. We've provided the LaTeX templates LaTeX file to the project. We will be filling it in section by section. And then first, please fill in the section of the write-up. Some tips are provided below, right? So basically, here we would parse the abstract, for example, and then give the instructions from the How to ML guide. And this, as the prompts before, also uses a combination of reflection and prompting, basically. Okay. Are there any questions to sort of the last two sections? Just making sure. Okay. Then I'll continue. Good. So this is how we essentially instruct the agent to write the paper. And again, like we're using the iClear template, for example, to create papers, but there are many other templates you could use, like, for example, the NURBS template and so on. And actually, maybe as an anecdote, as a side note, the actual writing takes quite a lot of time, right? So there are many API calls for each section, including reflection and so on. And this is something we spend quite a lot of time on working with. Next up. So here, this is now like just an overview of an example paper. So this is the paper or the idea and the experiment execution that I showed you before on dual scale diffusion. And you can see sort of there are various plots being implemented. There is LaTeX, so this is just at a glimpse. You can zoom into all of these things on the Sakana webpage, for example. But it's really capable of plotting results, running sort of ablations and comparative studies, drafting tables with different numbers, comparing the different configurations with each other, and also sort of writing equations out, for example, here for diffusion. So in many ways, to us, and this is maybe like an important disclaimer, this is like the GPT-1, or to us, this is the GPT-1 moment of sort of using, I guess, generative science, if you will, right? So many of these papers from sort of less powerful foundation models can have problems like hallucination and so on. But we're at a stage where this is only going to get better. Okay, so as model performance improves and as we pour more compute into this, we think that the quality of the papers will increase dramatically going forward in the next years. And if any one of you is skeptical, which I hope many of you are, I would recommend checking out the papers which are all accessible, right? So there are hundreds of papers which were generated, which you can look at and judge sort of the quality by yourself. I see there's a comment. As a novel task, has your group designed any automated tests or benchmarks to quantify the performance of this in future methods, or is there a plan to develop such a thing? Yes, Noah. So I spoke about this before, but I'm going to come back to it. We have worked on an automated paper reviewing pipeline using foundation models. And basically, this reviewer can sort of give numerical scores as well as sort of accept-reject decisions, which are fairly accurate. But I'm going to come to this next. It's a good question. Okay.
That's one problem with this generated paper, from what I can see. For 8-page paper, the reference section is rather short.
Yeah, that's true.
Like half a page of reference. So AI
No, no,
scientists
no.
are very keen on citing other people's work.
I think this is for sure like a limitation, but I think this is one that is actually also overcomable, right? So I think getting more citations in is something we're actually actively working on. And you're entirely right. Like, especially if one thinks about sort of the future consequences, then credit assignment is extremely important. Yeah, we agree. Yeah. Okay, there's another question in the chat. How can this AI scientist keep track of the updated references? You mean the references that we cite, how it can keep track of it? So basically, like the manuscript is in context, right? So it can see what it has edited, and it can see sort of what's in the paper at the current point of time. Okay, let me close the chat again and now come back to Noah's question, namely, how can we sort of validate or try to assess the quality of these papers, especially if we can generate so many so fast. So basically what we came up with is try to create an agent which can sort of do automated reviewing of these types of papers, right? So the way how this works is we take the PDF manuscript and we extract the text from it. So importantly, right now we're only extracting the text and we're prompting basically an LLM to perform a review as would be done at a conference, right? So we actually explicitly use the NURMS reviewer guidelines to essentially come up with key important aspects of a paper and have the LLM essentially write a review which conforms with NURBS guidelines. Okay. And again, here we also make use of all the tricks in the toolbox for prompting these systems, including few shot examples, as well as reflection, sort of ensembling reviews and performing a type of meta aggregation, but I'm going to get to that. But here, importantly, to keep in mind is that the reviewer is only seeing the text of the paper and not the images. Okay, so let me walk you through this crowded slide step by step. So basically what we're showing in the table down here is in the top 3 rows, the performance of essentially humans, a random decision and an always reject decision on 500 iClear22 papers, right? So if you remember, once upon a time, there was a NURBS consistency experiment, which showed sort of the same paper to multiple reviewers and tried to essentially validate or get a feeling for how consistent human decisions or human reviews are papers. And based off of this experiment, one can or we could construct sort of a human bench baseline for how well we're doing at sort of reviewing papers, right? So when you look at sort of the false positive rate and the false negative rate, they're not 0, right? So there are inconsistencies between humans. And what we try to do is essentially construct these LLM reviewer agents which can come as close as possible to the performance of human reviewers. And we considered sort of 2 different ways to do so. One is just sort of prompting the foundation model and extracting an accept and reject decision. So there's essentially a field that says accept or reject. And the other one is to use the overall score to essentially threshold for a given level into accept and reject, right? And what we find is that GPT-4o, using a one-shot example of a review and a thresholding at a score of 6, performs actually extremely close and in some regards even better than human reviewers at this decision-making task. Right? So as you can see here, the balanced accuracy of a human is around 0.66, while GPT-4o achieves something like 0.65. Yeah, and the reviewer here uses a combination of sort of few-shot prompting, reflection, as well as sort of ensembling different reviews, which are then aggregated by a meta-review. Yeah. So here, importantly, we're not making the claim that like human reviewers should be sort of replaced by LLM reviewers, but we're making sort of a statistical claim that for the iClear22 set of papers, which might have been in the training data, the GPT-4o classifier or reviewer is actually quite performant. And sort of to the point of whether or not these papers were in the training data, we actually found that it didn't perfectly ace sort of the reviewing, right? So in many ways, it seems like there might be they might not have been memorized in such a way that would make sort of overfitting in some sense a problem here. Okay, so here is an example now, again, for the adaptive dual-scale denoising paper, which we spoke about before, where you can see on the left-hand side, you can see a summary of the paper. So the paper introduces an adaptive dual-scale denoising approach for low-dimensional diffusion models, aiming to balance global structure and local details and generated samples, right? So this correctly sort of captures the paper's nature. And then we have a set of strengths and weaknesses, like, for example, one of the favorite weakness people always raise is that it lacks some types of theoretical justification, and that the computational cost of training this model is higher, which may limit practical applicability, right? So these things all make sense. But like I was already saying, there are essentially a set of numerical scores in here, like this overall score and the decision reject, which can be used to assess the quality of a paper, right? So this is sort of as good as we're doing right now, but in future iterations, we're sort of looking into improving this entire pipeline by using, for example, vision to also process graphs, right? So our working hypothesis so far was that good papers usually also describe the results shown in figures, and that the text might be at least sufficient for doing appropriate reviewing for the time being.
Are you
Are there any
creating the multiple reviewers scenario where different reviews are given and reviewers discuss? So AC making decision, are you creating the whole ecosystem, or right now just one review?
Yeah, give me 1 second. I'm actually looking at this. Exactly. So we try to sort of do more validation on this whole setup. And what I'm showing here, first of all, like I'm going to come to your question, Roseanne, 1 second, is sort of the performance of different models with different types of prompting strategies, right? So as you can see, GPT-4o is doing better than GPT-4o mini in adding reflection, ensembling, and sort of this one-shot example all help improve sort of performance up to 70% accuracy. Something else that we did to sort of look at the consistency was to look at whether or not the scores given by reviewers in real life, like here we sort of sample 2 human reviewers of ICLR 22 papers, whether or not the correlation between the 2 randomly sampled reviewers is actually higher or lower than the correlation of the LLM review score with the mean score of all reviewers. So basically, we wanted to see whether or not the consistency of the LLM with the human reviews was higher than the consistency of individual reviewers among themselves, right? And as you can see here with the R-squared, like the correlation coefficient is essentially higher for the LLM reviewer with a mean review than between 2 individual reviewers. Does that make sense, or does that explain or answer your question?
I don't know. Do you want them to be consistent? Because it's also important to have diverse reviews.
Yeah.
Yeah.
So
I think we want the correlation score to be high.
I mean, like to a certain degree, we wanted to show, first of all, that we can do as well as human performance, right? To a certain degree. But I guess if you think of it on a broader scale and you actually use the feedback given by the reviewers to improve the manuscript, right, you might for sure want more diversity. But like when you, for example, when one looks at the 5 reviews given, there is quite diverse feedback between the different reviewers, right? So yeah, it's a good point.
So in chat are asking or commenting if the LLMs are trained on mostly negative reviews.
If you mean because they're much trained or evaluated here?
There are more negative reviews out there than positive ones, perhaps.
Yeah, So actually, like we found that there were certain biases. For example, in Claude, Claude liked to accept basically everything. So there it seems like it's more positive, right? But like for GPT-4o, it seemed like it was fairly balanced in terms of its performance, right? But like for example, in the table here, we're looking at both balanced accuracy, so one where we normalize for 50% accepted and 50% rejected, and one where we're just evaluating on the unbalanced data, right? Because you're right. When you always reject, you're already getting like a 59% accuracy in the papers that we subsampled.
Yeah. Also, I'm thinking all these metrics are like average. You want to know how they're doing on average as a reviewer. But maybe what the important thing with science is you want to make sure you don't miss out the really, really good ones and you don't accept the really, really bad ones. I don't know. There must be a
I
metric
guess,
for that.
yeah, I guess like the false positive and false negative rate try to somehow capture parts of it. But
That, but
like,
also like if you rank all the paper by the true quality, just like the top, not just false or negative, but just like the really top ones you really want them to get through. And the
yeah,
middle great area, middle ones is like probably fine. Just because
yeah,
how science works, like you want the good works to be highlighted and the bad works if they exist,
yeah.
it's not great, but it's not going to be that damaging.
Yeah, as an anecdote, like we worked for a while on sort of like a rank-based tournament for reviewing, right? So basically where you always take two papers, you compare them against each other, and then you compare or you create some type of an ELO score, right? And then you can threshold based on sort of where you are in these rankings, whether or not you accept or reject. But this tended to work worse than just sort of using the plain review that you got out of GPT-4o. Mm.
Yeah, that is hard because unless two works are talking the exact same problem, it's hard to compare. Like, how do you compare sciences like art?
For sure, for sure. I agree. Like we were thinking about like sort of subsampling by field, right? But yeah, again, then it gets harder to create like a full ranking. And ultimately, and I'm going to discuss this later on as well, it kind of raises the question, what is a scientific contribution in the first place, right? What is sort of, how do we value scientific contributions? And yeah, I think this is a broader question for sort of the entire community to discuss going forward. Yeah. Let me quickly check. Can replace, but could it? Or could it aid humans? Yeah, so Matthew asks if it could replace or aid. So my personal view is that it will aid humans, right? I think with all of these sort of tools and agents that I've been discussing or introducing or talking about right now, in many ways, there is going to be human oversight needed, right? That's kind of out of the question. The question is only at what abstraction level, right? So, for example, like you could imagine that given sort of the overload of papers being reviewed right now, like an LLM review could just sort of be a first starting point for like a summary of a reviewer, right? But the best way how to aid humans is still to be discussed or discovered, right? Mm. But how does your prompt look like in the one-shot case? Yeah. Victor asks how the prompt looks in the one-shot case. So basically, we add a paper as well as a review written by us for that paper, right? So at one point, we used like the attention is all you need paper, but that is probably not the best example case because that paper didn't even win an oral or it didn't even get an oral at Neurospec. Apparently, we're trained mostly on reviewer 3. How good were the generated papers as judged by the reviewers? Yeah, we're getting there. You're asking a lot of questions. FYI, Medicare rates, one of its cost comparing how well it performs on each of these. Yeah, okay, that's a good point. Let me continue. Yeah, so now that we kind of spoke about every part of the pipeline, like starting from idea generation, experiment execution, paper writing, and reviewing, we're now sort of looking at some of the results more in detail, right? So basically here, we focused on 3 templates, one being a 2D diffusion case, like the one we showed before. One is basically taking nano GPT, and the other one is looking at sort of arithmetic reasoning using transformers and grokking. And we chose these three distinct subfields of ML because they kind of capture different parts of what we're interested in, maybe overall as a community, namely being generative models and transformer models, as well as sort of more scientific aspects of training neural networks. And here are, for example, 6 papers, or no, more than 6 papers, actually 10 papers, which we highlight in our report, which you can all look at online, where we sort of show that we can generate various papers which get a score of 5, which is like barely below sort of like a little bit below acceptance, and depending on thresholding, actually like a weak accept. And you can see sort of different ideas in sort of diffusion, but also in sort of using adapters, adapting learning rates, and also sort of looking at grokking and these types of things. And Thomas asks us any human review scores. So right now we haven't collected human review scores beyond sort of our own assessment of these papers, but this is something that we're kind of considering right now, or which is important as a signal for the community going forward. But as you can imagine, there are like many sort of ethical considerations and questions when sort of showing humans these papers and sort of using their time, right? So we're sort of considering how to do this the best way, but it's for sure important for the community overall to get a feeling for how well these papers perform beyond sort of the just automated review that we're looking at. Okay, I'm gonna go quickly over. Yeah, so these are
I love
some.
the question. Any insights why all the papers had the same title pattern? It's like something colon and a sentence.
Yeah, I don't know. Like, it's a good observation. Yeah, not all of them, or do all of them have it? Nah, the adaptive learning rates don't do. But yeah, I don't know. I wonder in my own papers.
Yeah.
I can't tell. Like some of them are actually quite funny and quite entertaining as well, I feel. But yeah.
So
Okay.
these papers are not just generated in writing, but also the experiments are done by the whole AI framework, right? So I don't know. I'm now interested to read the comparative study of weight initialization. Do you actually, or the AI scientists actually run all the experiments, and we have plots about like real plots of weight initialization difference in.
So we didn't check for all of the generated papers, but for the ones we highlight in the paper, we looked at the code and actually validated that the experiments were run, right? So yeah, so all the numbers generated in the plots are actually accurate. There were like some hiccups before in versions of the AI Scientist where hallucinations could happen, but we made sure sort of for the ones that we show here that this is not the case. So this is kind of all valid science to the degree we can assess. Yeah.
Okay.
Okay, let me try to get through. Here you can see sort of for the 3 sections or different subfields of machine learning, how well the LLM reviewer scores the papers generated by different foundation models, right? So we consider, like I said, Sonnet, GPT-4o, DeepSeek Coder, and Llama 3.1. This is the 400 billion version. And we show for like 50 papers each how well they scored ultimately, right? And as you can see, Claude performs best currently, and the open source model in DeepSeek is actually also quite competitive, yeah, when comparing, for example, with GPT-4. And sort of to give you a couple more numbers, here are sort of the total number of ideas generated by the different foundation models, the ones which were scored as being novel, and the ones that passed all the experiments and resulted in a completed paper, right? And then you can see here in these 2 columns the mean score as well as the max score and the total cost for essentially running these experiments. And overall, we kind of could boil down the price of doing research in this automated fashion quite significantly, and like on average, like even with compute costs, like most of these papers would cost around like $15, right? And the reviewer itself, for example, only costs like 20 to 50 cents. Yeah. Good. But that being said, like the quality of these papers is right now, I would say, at a medium medium stage. So probably like a workshop quality or like a really, really good master student. But there's still more work to be done in order to really get, I guess, something like a Nature paper in terms of insights and so on. Good. Here are just some of my highlights that I really enjoyed. So basically, there's no better feeling than opening up one of these papers and seeing a plot that you've never seen before. It's like quite the miracle moment, I would say. And here, for example, are images of sort of plots that the foundation model or that were not implemented in the base template and really sort of drove some message home, right? So here we have sort of these adaptive weights out of the paper that we just discussed. And here on the bottom, we have sort of a plot of a 2D diffusion model where different sort of weights are sort of color-coded, right? And sort of as a second sort of anecdote on the right-hand side here, we can see sort of an idea that's kind of dear to my heart, which revolves around using lottery tickets and pruning in the context of grokking and sort of investigating generalization when pruning these models. And more examples, again, you can find online. There are a bunch of bloopers from this project. For example, most of them highlight sort of the importance of sandboxing the experiment loop in the correct way. So we had, for example, the case where the model sort of iteratively, or not the model, the experiment file iteratively sort of called itself. So basically you had like a queue building up, which recursively grew, right? Which would have sort of crashed otherwise the machine. We also have an example where sort of the timeout out of the experiment. So we're using like timeouts in order to sort of shut down experiments which take too long, was modified by the foundation model. So the experiment could have run like way longer. But we also had situations where, for example, out of memory errors could occur when sort of checkpointing way too frequently. Yeah. Now sort of I want to sort of transition into like the final part of the talk where I just want to quickly highlight a set of technical limitations, future work, and also ethical considerations. So as we already discussed, the automated reviewer can be improved, for example, using fine-tuning or adding vision capabilities. There are many sort of ways how we should, as a community, work on further reducing hallucinations in sort of these scientific discovery pipelines, but also to verify the results. We also used fairly limited compute, so the experiment templates that we used are relatively small scale, and they can easily be sort of boosted up to larger projects if you're interested in these things. And then sort of, as I already alluded to before, to me, like a big question is how we want to go forward with communicating science, right? So what is a scientific contribution? And to me, usually this is much more about sort of how well does an idea diffuse into the community and how easily is it sort of deployed in own settings. There are many different future directions we're currently thinking about sort of to improve sort of the entire pipeline. And this includes, for example, iteratively using the reviewer feedback to improve the manuscript, but also the experiments. For example, automatically optimizing the agent pipeline. Song and a PhD student of Jeff Kloon's lab had really great work released this week on this. And then also to look at whether or not one can apply the AI scientist to sort of the AI scientist itself, right? Sort of doing a meta AI scientist approach, basically. And then I think most importantly, this slide sort of tries to capture some, but definitely not all ethical considerations going forward. So one thing, as I already alluded to, that's really important is to containerize sort of your experiments in the correct way to sort of be able to circumvent imports from libraries which are unknown or make sure that no harm is done, right? The other is that we all have to be completely transparent about how AI or foundation models affects our research. And in the papers that we release, we made sure that all of them are watermarked, right? So for example, it has to be clear that they have been generated by AI. And then I think one core element or aspect of how this is going to all play out is how we can make sure that the signal-to-noise ratio of these papers that are generated is sort of good enough that humans should spend their time on them, right? So I showed a couple of examples where I feel like, yeah, I would have read that paper. And I think going forward, we have to make sure that the signal-to-noise ratio stays high. I think I'm going to skip this slide for now. Something that I'm very passionate about, and what we also discussed all together, was whether or not we are going to see a future in which we're going to have fully AI-driven AI conferences, right? So this could include paper writing, paper reviewing, like a meta-reviewing process, an archiving process, as well as a communication process. And then again, sort of feeding back the insights into sort of the next fine-tuning or the next training stage of these foundations. And to me, this is like a bright future where humans are not completely taken out of the loop, but this sort of can do what they want to do, right? So there are many stages of science and doing research, which I particularly don't like, but I still have to do them. And I think sort of the tool set and the agent pipeline that I sort of presented to you today can at least in parts try to take off burdens from us when it comes to certain aspects of science which we don't like. Okay, and I think to me, this all sort of leads to like an open-ended perspective on scientific discovery. And I think there are many, many ways how the human can stay and will stay in the loop. Namely, for example, in sort of the context of, for example, like a pig breeder style approach to science, where humans are still in the loop in terms of deciding what is interesting and what not. But then the actual execution is one that is done by the machine or the AI scientist itself. Okay, and with that, just the final notes. You can find all the code online. This is open sourced. You can download this and sort of create your own templates for what you're interested in. And if you're looking to, or if you're excited about improving AI using AI, you can also check out a Sakana.AI and the careers page. Thank you very much for your attention, and I hope there's still a little bit of time to answer questions.
Cool, thank you. Just time check. Do you have to leave on the hour mark or?
I don't.
Okay, it won't take too much of your time. But
No,
let me stop recording so people can feel freer to ask questions.